Hello guys, we want to look at part 2 of work, energy and power, which is the last part. It's a technical aspect of it, which is we want to look at gravitational potential energy. We want to look at and conservation of energy. We look at energy in a simple pendulum, then power. Now, first of all, we know that F, you don't know, is equal to, let me talk about gravitational what? Potential what? Energy. First, we know that F is equals to what? Gmm over r square. This is the formula for gravitational force. Now, from the concept of what? We know that what? F can also be written as what? The V over the R. The V over the R. So if you cross multiply, you are going to have what? F the R equal to the V. So if you integrate this one now, let's say F is what? Gmm over r square dr equal to what? Integral dv. If you integrate it with respect to the v here and respect to what? The r here, you are going to have it as what? Because this one now, integration means what? You are going to have, this one is constant. So you are going to have what? Gmm into bracket what? 1 over r square dr. That's what it means. So you leave that one constant. It's equal to integral dv. If you integrate this one now with respect to r, which is same as what? R raised power minus 2 the r equals to integral dv. So what we want to have, gmm is still constant at the back. What we want to have is what? R minus 2 plus 1. You know how to integrate, add 1 to the power. When the power down, add 1 to it. So what we want to have is gmm over 1 is equal to integrate v. Yes, we would have v. At the end of the day, we would have what? Gmm over what? This one will give us what? Minus 1. This one will give us minus 1. So we would have minus 1. Then this one will give us what? R raised power minus 1 equal to V. You bring it down, what do you have? V equal to what? Gmm over R minus. Now, this minus sign indicates that what? It has a what? A reference what? Reference 0 as what? Infinity. That means that the motion travels from where? From what? That is, the motion is what? That is, the body moves what? That is, the body moves from where? From, or is launched from what? From infinity, which is a reference for the starting point, to a close point. A close point. A close point. Close point. That means from infinity to a close point. What I mean is that, let me take a circle. Let's say, look at the board. This is the earth. The earth. Look at the board. Technically, this is the earth. Now, this is the center of the earth. Let's say the mass of the center of the earth is ME. Or let's say M on the earth. Now, let's say the satellite is here before. Look at the board. It's here. Look at it. It's here. Now, we take having a what? A distance R1 here. Now, when you launch the satellite to a particular point here, this particular point, let me even call this place ME. And let's call this one radius of the earth first. Radius of the earth. From here to, from the center, this is what we call the center of what? Of the earth. Please look at the board. Why this one is what? The surface of the earth. This point, the center of the earth. Now, from the center to the surface of the earth is what we call RE. Now, from here, from where you launch it, this is the initial position. You now take the satellite to the what? To this position. Now, from here to here is what we call the H. Now, from here to this place is what we call what? R. This R is now what? What is our R? Re plus what? H. Look at the body. Re plus H. So more or less that this is R1, the initial position. While this one is what? R2. Let's take of that. Take note of that. Now, there is a potential change from what? V1 and V2. V is what called, this one is called what? Gravitational what? Potential what? Energy that we are talking about. GPE. Now, look at the body. If I move it from this position A, I move the satellite from position A to position B, what has happened? I have the potential change that have occurred is what? V2 minus V1. Hey, you have to get this in. Now, what is V2? V2 is minus what? Let's say mass of the earth and mass of the satellite. Let's take the mass of the satellite as M. Let's take it as M, mass of the satellite, over what? R2. Because is what? Is here now from R2 is final, V2. This is V2. Don't forget that this is V1. Now, minus, no, I gave you a formula here now. Look at the formula here. Minus what? GMEN over what? Over what? What is it? From here to here is what? Or from here to here, initial position V1. What is the distance? R1. Now, if I solve it, I'm going to have minus and minus is plus. So I would have GME mass, that is mass of satellite, over R1, because this one minus plus, minus GMEM over R2. So this is what we call the potential, which is equal to what? Potential energy. Now, this word formula can be written. This formula is what? Is the energy used to raise a what? A satellite or an orbit from what? A close, small distance or small what? Distance R1, which is equal to radius of the earth, to a higher distance R2, which is equal to what? Re plus H. So that means that for you to raise or launch a satellite from this point to this point, you need this gravitational potential energy. You need what? This gravitational potential energy to launch it to a higher height. Now, please look at this one. Now, what? Take it up. Something does not go up without you projecting it. So the velocity with which you lock the satellite up comes up with an energy called initial kinetic energy. Let me clear the board. Initial kinetic energy. It comes up with what? Initial kinetic energy. Now, this kinetic energy is what we call what? Half M what? The initial kinetic energy is what we call what? That means the energy to raise it up is what? Gravitational potential, which is this one. Now, sometimes they can write like this, which is the same thing as what? Potential energy is equal to what? GMEM over RE minus the same thing. GMEM over what? RE plus H. You can write it this way. It is the same thing. Please take a look. Where H is what? The altitude. That means from where? From the surface, the height from the surface of the earth. What is our RE? RE is what we call what? Radius of the earth. And that is what? 6400 kilometer. If they don't give you in kilometer, it can be also what? 6.0 times 10 to the power 6 meter. Don't forget 6400 kilometer. Kilo means 1, 2, 3. So if you have 1, 2, 3, 4, 5, 6. So that means 6.4 rather times 10 by 6 kilometer meter rather. Now, what about the R? R is equal to what? The distance from what? From the center of the earth, from the center of the earth to the satellite. So that means the orbit or the satellite has a distance from the center. Anytime they measure in gravitational field from the center, people always mix it up. From the surface, from surface to the what? So altitude is measured from the surface. Then from this center of the earth, if we assume this is the earth, so from the center to the orbit is what we call the radius. So they have a relationship that says R equals to what? RE plus H. Why? From here to this place is RE. From here, this is RE. From here to this place is H, altitude. So what is the total height now from here to here? Now what? RE plus what? H. That's how. So if you don't write it this way, you write it this way. Now, you know a satellite will be raised to a height. Now, the energy that you use to raise it to that height is this one. Now, for you to raise it to a height, there must be velocity that must be applied to raise it up. We call it what? The initial what? The velocity used to what? To launch the satellite is known as what? As what? Initial what? Kinetic what? Energy. Now look at it. It is what? Written as what? Half mu square. You take up that this kinetic energy. Now, listen oh. This energy is equal to what? This one. Because it's the one that what? That will help us to achieve this. So we can write it like this. Half mv square that you use to launch it is equal, hello, is equal to what? This particular one, potential energy, which will raise it up. The velocity used to what? Which is u. We call it the initial. The initial what? Velocity used to launch a satellite. What has an initial is as, let me put it this way. That like has an what? Initial kinetic energy, this is this one. And that kinetic energy is equal to what? GME over what? RE plus what? Or minus, which is this here. Look at it here. GME over what? RE plus H. Please take note of that. What is the potential energy here? To take it to a height, to raise it from this initial to what? Now, what is this particular one? Is the energy that comes in to help to what? To raise that. The kinetic energy, because it's moving up. The energy, the motion, the energy that comes as a result of movement from this here to this place is what we call this, and they are always equal. So, what is your U? U is what? Initial kinetic energy, which can be calculated by what? M is common on all three, so we can cancel out M is common, which is now be U squared equal to 1. GM is common, you have got 2, multiply all 2 by 2. That means these 2 multiply everything that factorize here. GME will be factorized common, 1 over RE minus 1 over RE plus H. So what do you have? How do you make U the subject of formula? You what? Take square root of both sides, which is U is now the what? Take square root of both sides. Now the what? Square root of 2GME over what? 1 over RE plus minus 1 over RE plus H is a formula that you should not play with. Very important formula. So this formula is what we use, the velocity that we use to what? Raise the satellite to that particular height. But it is possible that the satellite does not return. This is a very vital information that you need to get. Now, if the satellite is launched with this that velocity that you use to launch that satellite, let's assume that it does not return. If it does not return, it means that the kinetic energy, which is what? The kinetic energy, which is this kinetic energy used to raise it up, to launch it, is greater or equal to what? Potential energy. So if the satellite will not return, and that means that body you launch, that you raise with this velocity, if it will not return, that means that the kinetic energy is equal to or greater than potential energy. Let's take equal to have the minimum what do you call it, velocity that will be given to the body. Let's say this one now be half m what v square equal to what? G, this is gravitational potential energy. Please don't forget. I told you that for what? This one now will make the body escape from what? From the earth. This condition. So it will make this condition given to us, will make the what? The satellite escape from the earth permanently. They will never return. But if what? They are also equal, it is possible they are equal. So gravitational potential energy equal to kinetic energy. That is the minimum what velocity that can be launched, which we call the escape velocity. And that will give us what? G M E N over what? R. So this is the minimum what? Velocity that can be applied so that the kinetic energy to raise the body should be equal to potential energy. Although if you see escape, that's how we are calculating for escape velocity. This is escape velocity. So this mass we cancel mass. What do we have next? Now we have what? V escape square equal to what? 2 GME over R. So what is the escape velocity now? Now the square root of what? 2 GME. Don't forget our R is equal to what is our R? RE plus H. So this is what we would have as escape velocity to escape. But what about if it does not escape? If it has to return, if the satellite or the orbit or the object have to return back to the earth, it means that the kinetic energy must be less than what? The potential energy. Please take of that. That means the kinetic energy used to launch the satellite must be lesser than or smaller than the gravitational potential energy. It must be lesser than what? Gravitational potential energy. So take note of that. Very important to note that. So it must be lesser. Now, the next thing that I want to ask you now is this. Now, when you have launched it to that point now, it's now there. It's there at that height now. Look at the board. It's not there at the height. Look at the earth here. This is RE. This mass of the earth from here to here. This is H from here to here. This surface of the earth, the center of the earth. Now you have launched it. Now to remain here, to remain in that position, oh God, you need to get this thing. To remain in that position, that means to now orbit that particular earth at that position, because now we have raised it up. Now we are now here. What will now happen? We need a what? A mechanical energy that is constant. That the total energy to remain in that position, to orbit, what we call orbiting velocity, is equal to kinetic energy plus what? Potential energy. We call it what? The total. Now that total is what? What is this one? Now kinetic energy, don't forget that mv square over r, it must be equal to what? Me over r square. Now to orbit here, to remain here, the centripetal force must be equal to what? Gravitational force. So in that case, this will cancel the mass of the satellite. What will happen now? The r will cancel out the remaining 1r. So v square, or no need to even cancel it. Let's not cancel it. We are not stress ourselves. So we have mv square over r equal to gm, gravitational potential energy, over r square. If what this me, this mass of the satellite, if this one cancel this one, now what will happen? Let not cancel that one. Sorry. Let me cancel this. So that we now have what? Mv square now. Abi? If you cancel, leave this one is not cancelled. is equal to what? Gm what? Em over R. Remember that kinetic energy is equal to what is kinetic energy? Half mv square na abi? So what will now be? Half what? G what? In place of mv square, what do I replace it for? Me over what? R. But remember our R is what? Where the radius of the earth, altitude and radius of the center. So it now be what? Equal to what? 1 over 2 GME times M over what? RE plus what? H. That is it. That is the kinetic energy. Now, what is our potential energy? We have already, this is our potential energy I gave you. Now, total energy to remain in orbit is what? What will now be? To remain in that orbit, I will now combine the two of them together. What do I do? Look at it. I will combine the two of them together. Look at it. So if I combine the two of them together, what do I have? If I combine, I will go to have what? Look at it. This is what? Kinetic energy is equal to what? Half GMEM over RE plus H. Then potential energy that we have just what? To launch it, to raise it to that height. I believe very common. MEM over RE is mass of the earth minus GME mass over RE plus H. If I combine these two and put it in what? The total what? Orbiting what? Energy is now going to be what? What do you have? I will have this one half GME M over RE plus H minus what? Plus what? GMEM over RE minus GMEM over what? RE plus H. Now, what will now be final answer? We are add it together now. This and this can be added. 1 over 2 minus 1. Because this and this have the same coefficient. The same, this is the only thing, they don't have the same coefficient, but they have the same 10. But this one have minus 1, this one have half. Abi? So if you add it, this is what? Kinetic, and this one together is what? Potential. Now, what do you have now? To launch it now. The total energy that it will possess here. Yes? This one and this one will give us minus what? No, just minus 1 over 2 now. Abi? So GM. Now listen, wait. This one is total energy I'm calculating. Total energy, not the energy used to orbit. This is total energy. Total energy, because energy to raise it up plus energy that it will possess when it's there. You understand what I'm saying? This is total energy now. What is total energy? Kinetic potential energy. Now. Okay now. So that is what I'm calculating. Total energy. E total. I even wrote it here. So this one had what? ME over what class now? RE now. Minus. You know why it's minus? Because half minus 1 is minus half. Half GMEM over what? I hope you still remember that the total energy is equal to what? Potential plus what? Kinetic. No, this one is not total energy at what? At this point. Oh. This one I'm calculating total energy in the entire system to raise it up and to remain in that orbit now. Look at the board now. Look at this. Look at now the board. Do you know that F equal to what? GMEM over R square. Which is the same thing as what? RE on the earth surface equal to what? Mg. This mass of the satellite, mass of the earth, radius of the earth. If this one cancel out, what will happen? That means GME is equal to what? GRE square. Now? Yeah, let's substitute. Anywhere you see GM, let's put GRE square. So what do you have? GRE square times M over RE minus what? 1 over 2 GR what? E square M over what? RE plus H. So what do you do? This one can cancel out this now, abi? So what do you have? Yes, E total will now be what? Will now be what? Total energy. So E total is now equal to what? G RE times what? M, abi? Open bracket, or what's called the M. You know what this mass mean now? That is mass of the satellite, abi? Uh, over what? What remain here? 1 minus, abi? Everything have been removed. No, I cancel this one, remaining 1 R now. So I've removed MGRE. So nothing is remaining here now. But if I remove MGRE, what will remain there? Will now remain RE, abi? That is what remain now. If I remove MGRE, this one remain R over what? 2 back at what? RE plus what? H. This is the total energy. Total energy in launching is what? A satellite. Total. First of all, there are two processes to launch. Take it up and the one that will make it to remain there. You take it up and the one that will use what? To remain in that what? Height, altitude. But what you need, most schools cannot ask is that they can say, what is the orbiting kinetic energy? That's the last thing I'm giving here. Then, what is the what? Orbiting what? Kinetic what? Energy. The orbiting kinetic energy what is what? The is equal to the potential in that orbit, which is what? GMEM over RE plus H minus what? Plus, because when you take it to a particular height, it become RE plus H. Then the kinetic energy, I've given that formula before, is here. Look at it here. It's still here. Okay, look at it here. Plus what? GMEM over what? 2 RE plus H. If you add these two together, it will give what? This is the potential at that height. When you launch it to this place, now this position. This is what kinetic energy at that position. When you add the two of them, kinetic energy at that height is already in the orbit now. It's already there. So the orbiting kinetic energy will now be what? If you add these two together, I would have minus what? This minus 1 plus what? Minus GME over what? 2 E RE over plus what? H. This is what? Orbiting what? Kinetic energy. This is it. Now, I've given 3 formulas. Circle them. This is very important. Now, what is this one used to raise it from a particular surface of the earth to this way, to raise it? This one can be taken as R1, this one can be taken as what? R2, because it's what this R1 is where it was here, initial position, R2 when it was here. So this to raise it. Which of them is what? The velocity used to launch it, because it cannot just go from here to here. It is not spiritual. Something must what? Raise it to that point. That velocity, that energy to raise it up is what we call what? The half m what? U square. Initial kinetic energy, which is equal to what? This one. So you can solve for this velocity by equating these two. I've talked about it. Even when if this kinetic energy project with a what? Initial velocity that is more than, if this kinetic energy is more than the potential energy, it will escape permanently from the earth. If it is equal, that's what we use to calculate escape velocity. When this potential energy is equal to what? Gravitational potential energy, it will still escape to produce what? The escape velocity, which is the minimum velocity required for a satellite to escape permanently from the earth. But if it is less than the what? The potential energy, it will return back to the earth. That is the 3 scenario you can have. Then this one is what? When you stay here, What is the orbiting what kinetic energy that we use to maintain this particular position to remain in that orbit is what it is for. What is the total energy both the one to launch and the one to remain at that orbit? The total energy is it. So take note of that. The total energy, this is orbiting what kinetic energy to remain in that orbit, what, and this is what the energy to raise it that what a particular height. I believe I've solved. We've talked about what this one is clear now. Now the assignment I'm going to give every one of you that are watching this video is what is question is what the formula. What is the formula for what gravitational potential? And what is the unit? Please type your answer in the comment section. What is the unit? What is the formula for gravitational potential and what is the unit? Now, conservation of energy says what energy can neither be created nor destroyed but can change from one form to another. Now, in an isolated system or a closed system, the mechanical energy is constant, meaning that the sum of the potential plus sum of potential and kinetic is constant. Now, it is applicable that most systems conserve their energy. We have two types of systems that we're going to consider here due to their forces that they influence. We have what they call the conservative force and the non-conservative force. Conservative force are what forces that act on a body and what push a body round a trip to make their work done to be equal to zero. Move a body through what a trip. That means they act on the body and ensure that they move the body round a trip and to make the work done to be equal to zero. Example of such is what gravitational force in strings are good examples of what conservative force. While non-conservative force are forces that do not what when they move out on a body, on a system or on a body, they do what when they do not what move the body round the tree to make the work done to be zero. So they did not cause what the body to what. They have seen question like that. They ask one question like that in the what. They ask the question. They said what? Look at the question they asked. They said past questions that we have seen. They talk about. They said differentiate between what conservative force and non-conservative forces. Now, the work done by the force in moving a body round, through what round a trip is equal to zero for conservative, but the other one for non-conservative is not. Number two is that the examples of what of conservative forces is that they are gravitational force, reactional force, force in a string, and etc. and etc. But non-conservative force, we have frictional force is a good example. Now, in conservative forces, the mechanical energy is constant, that means is conserved. But in what? In non-conservative force, mechanical energy is not conserved, although the energy is conserved, but the mechanical energy is not available in such a system because they are converting their mechanical energy to heat energy. Look at what happened. That means the kinetic energy plus what? Gravitational potential energy before and kinetic energy after plus gravitational potential after plus Q. Where Q is a loss of what? Of energy due to heat. Lost the what? The energy. In this case now, that the mechanical energy is lost as heat in what non-conservative energy. So that is just that. Another thing again we have to talk about is what? Simple pendulum. You can learn more and talk about more of that here. Simple pendulum. Now when we talk about simple pendulum, energy is simple pendulum and power. Then we'll round up this. Now this is what simple pendulum. Now this is what, let me take one side of it and analyze it. Now this is suspended on the ceiling with an angle theta. Now this is, let's say this is the length of the, don't forget the length of the string. This is an inextensible string. This length here is also what? constant here from here to here. For the fact that it's moving from equilibrium position to B does not mean the length will change. So in that is the length of the constant. Now let's take from here. Now if you resolve this length, this length now, this length, because look at this is 90 degrees. If you resolve this length with respect to this angle theta, then we have from here to this level now the word L cos theta. Please take of that. Then the height, there is an height that this one has moved, h here, from here to this place is h. That is h. So h plus what? This one, that means from here to here plus from here to here, L cos theta equal to what? L. So what do you have? I want to have h equal to what? L minus L cos theta is equal to L into bracket 1 minus what? Cos theta equal to h. What is the potential energy possessed here? Because it possesses potential energy here, but kinetic energy here is 0. But here in equilibrium position, kinetic energy is 0. For potential, kinetic energy is maximum, potential energy is what? 0. Now, what is potential energy at point B, which is extreme position? Is mgh. So the work done equal to what? Potential energy, which is equal to mgh, which is equal to what is your h now? The length of the inaccessible string, which is what? Mg, length, open bracket, what? 1 minus what? Cos theta. So this is what? The energy possessed in in a simple pendulum. The last one, which is power, to call it a day, which is power. Power is the last one. Somebody say power. Power is the rate at which work is done. Power is the rate, last one, at what rate of what? Of doing what? Work. Power is real. I mean, power is equal to mathematically equal to work over time. It is measured in joules per second or what? Watts. It's about watt. These are standard units of power. So power is what? Can be what? Half mv square kinetic over time. Power can be mgh over time. Power can be force times distance over time. Distance over time is velocity. Force times velocity. Power can be half mv square, half ke square over time. Power can be half mv square minus half mv square over time. And so forth and so on. You can think of what? Other formulas for power. So all the work done formula that I give it to you. In fact, power can be equal to what? Force times distance times force times distance over time. That means F cos theta over time. Right? This is work. Now, when it's an inclined body, when the body is inclined at an angle to the wall, the force is inclined at an angle of theta to the horizontal. We have talked about this one. So look at it. So what is the work done here? The work done is F cos theta times distance moved by the body inclined by the force applied, distance moved by it over time. So we can have a lot of work formulas for power, but I believe I should end it this way because we have tried so far to explain work, we have explained energy, and we have also explained power. And I believe that the more you watch this video, the better you become and the stronger you become. Just make sure you watch and ensure you like the video. When we solve question, we have done with part 1 and part 2, which is work, energy, and power. Once we solve question, it will now become clearer and better. And I believe that God will give you knowledge and understanding to be able to comprehend this video better, even beyond what I have done. Thank you very much. God bless you. Wisdom is profitable to direct. Enjoy your day. Thank you.